Alrighty, let's start. About half an hour ago, there were only 30 returns, so only 30 names on the returns. It means that about 15 of you have not returned the first exercise yet. Please do it, preferably today, because there will be a penalty on late returns. Another thing, I just noticed that my exercise 1.m did not actually function for some reason. So I changed the permissions to link. Does it work now? Have you tried it, say, lately? So of course it works for me. So if you click on the signals and the MATLAB command history file, does it open it now? It does. Okay, good, good. And it opens only if you have logged into your Metropolia Google account. Okay, good. What else? Yeah. Yep, so the signals, as you can see, the return was already 2 hours ago. Haha, evil. So today's topic is about systems. And let me first see if my stream is actually working. Yes, it is. Excellent. Let me first see if my stream is actually working. Oh, great. There we go. Same procedure as last time. So first I give you some background on the theory. How many of you have actually accessed this DSP guide from internet? The textbook I mentioned last time. It might be a good idea actually to take a look at that one. It's up to you. But anyway, so last time we had the digital signals. May I have your attention, please? Okay. It would help me concentrate if you actually follow this way. Please, guys. Okay, thank you. When you're talking about the system, it means that okay, a digital system is something that makes calculations. So on digital signal processing, most of the systems can be actually done by using only 4 basic operations. That's not much. So it's addition. Okay, you add signals together. Then scaling, meaning that multiplying by scalar number, just the ordinary number, constant number, meaning you're actually multiplying by the signal by constant. So in electronics, that will be the same as gain of amplifier, exactly the same thing. Then we have the delay, meaning the how many time steps delay you put to the signal. Or actually, there's also negative delay, meaning the advance operation, meaning that you would know the forecast of the signal for sure. Of course, you cannot do it. But on post-processing, that's not just a nice trick you can play. So if you have tabulated data, then you can do also the negative delay. Then we have a multiply of signals. So multiplying signals, it's the same as mixing. On your RF design course, you probably have already gone through this. How to make a FM modulated signal, where you have the your data signal going to one input of the multiply, and then you have this just a sinusoid frequency, the carrier frequency going to another one. You multiply those, you will get the FM modulated signal more or less. Oh, that would be amplitude modulation actually. Sorry about that. So 4 basic operations. That's where the digital signal processing blocks, most of them are done. Then few things that are pretty important to understand what they actually mean. Linearity, causality, stability, and time shift invariance, what they actually mean. The first one, the linearity, is a nice property if you are having a, say, a system that you can predict what is the output. So it means practically that we have a superposition principle can be applied, meaning that if you know one type of signal output, then you can actually derive, based on that one, you can derive also the output for the other ones. Or summing the signals together in input is the same as summing it on the output. That's the linearity. So linear systems are additive and also the, what was the other? Commutative. Okay. Pretty good property for basically any system. Predictable system. Good example for linearity would be the, let's see. Okay, a linear amplifier. It just amplifies the input signal, that's it. As long as you're within the boundaries of the operating system, operating voltage. Okay. Causality. Another kind of property that's important to understand. Basically, it means that there is no action, or actually there's no reaction before some event happens, meaning that the system cannot forecast the future. A human being is always looking at the future. For example, if I would start talking really weird here, you would probably start going outside since it's getting weirder or weirder. Okay, a good example. So people are non-causal. We can predict a little bit on future. That basically saves us from lots of trouble. But basically, most of the, say, digital systems are causal systems. Parking meter, for example, it does not give you the parking time before you put the coin there or use the app to start the parking. You cannot do it, afterwards. But okay, in some cases you can actually pay it beforehand, so that it wouldn't be a causal system. Third one is about stability, and in digital signal processing, stability is thought as the bounded input, bounded output stability, meaning that if the input signal is within some limits, then there is also limits for the output. Again, good property, for example, for the linear amplifier, meaning that if you give a linear amplifier, okay, the input signal is less than 100 millivolts RMS, then you would know that, okay, now it does not saturate, but the signal is just amplified. Okay, so stability is also kind of a nice property for, say, natural systems. The fourth one is about time shift invariance, meaning that the system does not change as a function of time. So behavior does not depend on time. Parking meter is actually a good example of good system which is not time shift invariance. Otherwise, you would be paying also for parking between, was it something like 7 p.m. and 7 a.m. So it changes, the system changes the properties when it comes to this basically evening and early morning hours. Okay, but we have some exercises on that one. I will go through all those. Some properties. Basically, for the digital systems, linear and time shift invariant systems are the ones that are used most. Though, for example, all the digital, well, most of the digital filters are actually linear and time shift invariant. Are they also causal? Well, only if you can use them as the, say real-time systems. If it's post-processing only, then it's not causal system. Stability of the LTI systems, we will have some tools for that one later. But the nice property of these linear time invariant systems in digital domain is that you can actually write this the formula to calculate the output, so-called difference equation. So basically, difference equation can be used to calculate the output value, as long as we just know the system parameters or system coefficients. So basically what this upper form shows is the one way of showing the difference equation. It has the weighted sum of the output and the history. Okay, so there's yn minus k, where the k actually goes, the time delay goes from 0 to some number n. So basically it's a weighted sum. Okay, so what? We will practice on that one. So that's basically the output, current output and feedback term. On the right-hand side, we have the current input value and the history, and just a weighted sum of that one. So all linear time shift invariant systems can be represented by that kind of formula. Okay. So for example, have you tried suppressing some noise with the running average filter? Yes, you have. So that's the first thing you try to do, is to try to suppress the noise. It is okay. So it actually will cut off these highly varying components of the signal. Not all of them, but it reduces the noise level based on the well-known statistical fact that the variance actually goes down by the when you take the numbers, and then, well, it's 1/square of the number of samples should actually affect on the how much this average has variance on it. Okay, but that's statistics. You should know that from the first year and remember it really well, right? Okay, the same difference equation. Yeah, that's a difference equation if you take a look at the lower form. So you have output is the sum, weighted sum of input and its and the delayed terms, and here we have on the upper part, actually we have the 4-point running average, meaning you are taking 4 data samples, calculate the average, and then move to the next 4 points, and so on. So definitely that's a formula for that one. On the other hand, you then basically are losing something on the performance side, since that equation takes three additions in addition of the multiplying. Okay, the multiplier can go out as a common multiplier, but what is inside, you still have sum of 3. But if you are using the previous value of that, the previous value of the output, you can actually go and subtract the latest value and adding the current value to the running sum. So practically, you would calculate this more efficiently by first initiating this running average and then start updating it by taking the oldest value out and adding new value there, and then calculate the running average that way, which is more efficient way of doing it. On this case, it's 4-point running average filter. We have only one calculation less here, but think about 100 points, where you would have 99 additions compared to this formula, which is still the same. You would have just the difference on, well, 2 parts, the multiplier and the delay. So only 2 additions and 1 multiplication required. Okay, so feedback definitely helps on the calculation performance in this case. So anyways, it also shows that the difference equation is not a uniform function. There are different ways to calculate the same output. So it's not unique formula. It's a formula to calculate the same result. Same actually goes with the block diagram. While this formula actually gives just one way of calculating the answer or output, the block diagram or flow chart, that actually gives you the implementation, meaning next step from that one would be code. For example, here, if you think of this kind of block diagram, this would definitely waste some resources. We have 4 multiplications of numbers with the same multiplier. So doesn't it make sense actually move the multiplier in front as a common multiplier? Still the same difference equation, still the same output for the same input. Okay, one step forward. There's also the feedback version of it. So as this one had the same amount of additions, but the middle one has less multiplications, then we can also do the same in this sort of loop. So whatever comes in, we first scale it, and then you can basically just follow this one and have the delay, meaning the memory. You're just making this into the memory locations. On the programming, did you actually go to the ring buffer? Do you remember ring buffer from the programming? Okay. ring buffer, that's where you use a ring buffer. Ring buffer would be a good place to save this certain amount of data without need of shuffling the data around. But anyways, that's just a kind of extra curriculum thingy. Okay, and then we have the addition, which is actually subtraction. So addition is just a side, subtraction is just a side addition. So this is minus, and then we have the feedback term. So yeah, something like that. Yes, and plus here. So when you follow this signal flow on the block diagram, you can actually find out, okay, the yn equals 2, whatever comes here, plus whatever comes here. So we have that one, and then basically, okay, looks like that one. And while this difference equation should just, this multiplication should be done separately for here. Well, on real code, you would just have the one multiplication of the input signal. Some deep memory to remember some of the previous values. So this is the fourth history of the fourth previous value, and then 1 time step delay. So you just need to remember what was the previous value on the output. Okay, quite efficient. Okay, so block diagram. So we have the difference equation and block diagram. Both are on time base. Kind of easy to program and understand. More or less straightforward. You can, after doing the block diagram, you can start writing the code. Transfer function. Yeah. On digital domain, there's also transfer functions. Remember making some Laplace transforms and analog systems where you can analyze the system by making the Laplace transform of input and then multiplying with the transfer function of the system. That gives you the Laplace transform of the output, which is easy that way, but then you start trying to figure out what was the inverse Laplace transform for the output. That was the hard part. It's not that hard in digital domain since we do not need the inverse Laplace transform. So we can always do the calculations on the time domain. But for the analysis, we still need the transfer function. And the same way as in analog signals or systems, the transfer function is a complex frequency domain function, and that one describes the system behavior uniquely. On continuous time, we had the Laplace transform, which probably you all love, especially the analysis. In discrete time, we have the Z transform. That probably has been already on one of the mathematics courses. Usually it is. But, okay. Last time I think we covered a bit of the convolution and correlation and that kind of stuff. So now we actually come into the interesting, well, interesting, at least me it sounds interesting. So how to do filtering. So what that one says, convolution between impulse, response, and input. Wow. So basically we can calculate the output if we can just have the impulse response and multiply that, to convolute the input signal with the impulse response, that will give you the system output. Okay, we had this basic signal impulse last time. An impulse response is nothing more than just have the impulse signal going through any system. That's your impulse response. Nothing more into that. What does it say here actually is that, okay, if we have any input, feed it through the system, we get that arbitrary output. But on the this Z-transform space, actually we have Z-transform of output is equal to Z-transform of impulse response times just ordinary multiplication, no convolution, times the Z-transform of that one. So basically, this is your transfer function. So transfer function is actually quite tangible thing in digital domain. It's just the Z-transform of whatever comes out when you put impulse in the system. So now we have some predictable values as long as we have linear time invariant system. Okay. Back to the transfer function. So some important properties similar to the Laplace transform. This the linearity. Okay, Laplace transform was linear transformation, meaning it's you can apply the superposition principle. Time shift. Okay, same thing as in the analog domain. If we have time shift, it comes out as well, just a little bit different. So there is that complex number z to the power of minus k, or whatever this time shift here is, like that. Then unit impulse and unit step. What is the Z transform of unit impulse? That's 1. Or unit step, okay, Z divided by 1 plus C. All right, so basically where to use this one? It actually just states that if you have the, well, it just states basically that fact. And this one, what it does give you is the way to calculate the digital domain step response and then compare that one with the analog system, corresponding analog system. Wow, that's a lot of, sorry about this formula kind of thing, but actually this is a, say, maybe the most important formula of all. Just a little bit clearer. So if we have this difference equation, sum of k, index k from 0 to n, we have the a k, which is just a system coefficient or system parameter. If it's a filter, then it's filter coefficient, times y n minus k equals to k from 0 to n bk times x n minus k. So this is the difference equation of any linear time invariant system, same as I showed earlier. The transfer function, corresponding transfer function for this system is, okay, sum of okay, from k from 0 to n, bk times c2 minus k. So that's the transfer function. The numerator and denominator actually is k from 0 to n, a k times z2 minus k. So transfer function for any digital system, linear time invariant digital system, actually has exactly the same coefficients as the difference equation. Nice. That makes life much easier. And please note, this is one of the most common places to make mistake and lose a point on the exercise. The multipliers or scaling factors of output are on the denominator side polynomial. And scaling factors for input are actually on the numerator side of the polynomial. Okay, now you have been warned. Some of you will make the mistake and lose some points. Okay. I also have done a couple of times that mistake and lost some points. All right. So, yeah. So I have this example of the 4-point running average filter. So I have the their output, this without feedback term. Output is a quarter of x4, xn, and so on, which gives basically, if you just compare these two, I have made z transforms, but anyways, if you just compare this form, you have actually, let's see. So we have y of n times, where's the sum? Okay, we have k from 0 to 0 actually. So we have one term here, meaning that we have number 1 on the beginning as a multiplier. You always have that one as the one of these terms. And then we had the sum of k from 0 to 3 1/4 times x of n minus k. Good. Which means that z transform, or system transfer function is simply, okay, that one, k from 0 to 3 1/4 times z2 minus k. So we didn't make mistake here, divided by 1 times z2 power of 0. So this one here actually is 1 times z2 minus 0, okay, plus 0 times z2 minus 1 plus 0 times z2 minus 2 plus 0 times z2 minus 3. Okay, so we have basically those corresponding, if you compare this one directly, you have the corresponding the highest order number here, always the same, or almost always the same. Okay, good. And we got that one. On the other hand, if you take that, okay, and multiply it with 1 minus z2 minus 4, and divide it by 1 minus z2 minus 4. Oh, sorry, not 4, 1, hey, minus 1. You actually get one plus z. Okay, I think I have a mistake here. Which is corresponding to the feedback version of our difference equation. So yes. These brackets here. Okay, this is a transform. So in theory they can be either or, but you know it's just my way of marking this is a transform, not a regular function. Oh, just regular brackets. Yes, thanks. I will do some editing then. Actually, they don't need to be those brackets. Just ordinary. Yeah, thanks. Now I should make notes. Hey, could you go and click and leave a comment about those brackets? If you open that page, you should be able to leave a comment. Then I remember. Okay, so yeah, most important part probably on the course is actually understand this system coefficients or system parameters. The filter coefficients are exactly the same on the time space and frequency space. No need to shuffle those. You just make the design on frequency space for filter, for example. Then after that, you know exactly how to calculate the output of a filter in time space. Good. Wow, that wasn't all. Again, this here is practically nth order polynomial of z. So you can actually write this one then by basically multiply and divide it by z to n. Other way around, sum of k from 0 to n. Make this positive polynomials of z. bk times z to n minus k divided by k from 0 to n ak times z to n minus k again. Okay, that's a positive polynomial, a positive index polynomial, meaning that both the numerator and denominator polynomial has roots, meaning that you can actually show this one also as product form. Some, constant, which is, b0 divided by a0, or maybe I should actually put it here. b0 divided by a0, which is common multiplier, times product of k from 1 to n, z minus zk divided by product of k from 1 to n, z minus pk. Yeah, And basically, the okay, let's see how to mark it. pk here, those are the roots of this polynomial, and they are called poles. Similarly to analog systems, the transfer function had special points called zeros and poles, especially the poles. We have these polynomials also have zeros and wrong color. Zeros and poles. Zeros of the system are the polynomials, the roots of the polynomial, which is defined by the this numerator side coefficients, and poles are the roots of the polynomial of the denominator. Wow. And that B0 divided by A0, you can think that as the system gain, overall gain. Okay, graphic representation. Sorry about this picture, something has been kind of lost there. On the other hand, this could be also a system, not really any say good system, since usually you would put the zeros, which are the circles here, you would put these exactly on the unit circle. Let's find an analogy from the analog world. On analog world, you have S-plane. Complex plane, J here, this is real axis. This was if you have the pole on this region, then you would have unstable system, right? If the poles are here, then it's stable. And if I draw a circle like that, J omega C minus J omega C, so the radius is omega C, and mark a couple of poles like this. Recognize the filter. It's a low pass type Butterworth filter. Right. Have you done this kind of diagrams? Yes. RC filter, you have single pole here. Or if you have more RC filter, more stages on RC filter, then they will be on the real axis. But on those Sallen-Key systems, you can actually put these poles so that you would get different kind of properties for this passband. Alrighty. Similar picture on Z-plane. Looks like that. No more. Well, we still have the real axis and imaginary axis, but the frequency is not anymore on the imaginary axis. Frequency is actually the angle. So if this was a angle or complex angle omega, then the point on unit circle would be the e to j omega, and that is linearly proportional to the real frequency. There are some exercises that you will probably get a feeling of what it actually means. But currently, you need to know practically if we have these zeros and poles of the system, then they would actually be somewhere around the poles would be usually inside of the unit circle, because all of that is unstable to put the poles. Same thing as here. If you put poles in here, you would have oscillator. And actually, with some gain, which is usually not a good idea. It saturates pretty fast. And then we have these zeros, and if we had this corresponding analog filter in digital domain, then you probably would have double zero at that point, for a good reason. That's basically the highest frequency that you can represent. This one here is where the omega is pi, corresponds to sampling rate over 2, Nyquist frequency. The highest frequency you can actually represent. In here, the highest frequency is on infinity or minus infinity, where low pass filter output goes to 0. So basically this starts to make a little bit of more sense. Anyhow, well, with the MATLAB or Octave, then calculating the zeros and poles is a walk in a park. There are mosquitoes, and then there are some angry dogs and something like that. Rain, sleet, whatever. Okay. Anyhow, so you have these system coefficients on the output and the memory, so history, or system coefficients for the input and the memory. Same system coefficients actually go into this transfer function, so they work in time domain and a frequency domain. On frequency domain, you can also calculate the roots of those polynomials. So it's the upper part is the numerator polynomial, lower part is the denominator polynomial. It has zeros on the upper part and poles on the lower part. Calculations later. Okay. Real axis, okay, there are some animations. Wow, unit circle, multiple pole, system gain. All right, so how does our example system, which is 4-point running average, actually relate into this one? Well, yeah, you can calculate the zeros and poles simply by doing some simple calculations. You can divide this one into, well, it's third order polynomial. You can divide it into basically the product of two different polynomials, z squared plus 1 multiplied by c plus 1. All right, so zeros are minus 1 is the pole for that, 0 for that one. So you just mark z plus 1 equals to 0. That gives you minus 1. Z equals minus 1. Okay, that's one of the special points. Then you mark c squared plus 1 equals to 0. You can say, okay, z squared equals to minus 1. It means that it has the imaginary unit and plus minus imaginary unit as the roots. Okay, poles. Quite simple. You mark z to the power of 3 equals to 0, which is the that form you had. You multiplied it c to 3, c to the power 4 for yes. So the highest polynomial is actually Z3 there, and you will get actually these three triple pole at origo. So there are always three roots for third order polynomial. Remember, we are now on the complex plane. On real plane, then there would be only, for example, here you would have only one root, but okay, this is really just a complex number. And where did we need complex numbers on this analog world? Basically, it's about the phase angle of the. Without the complex angles, you cannot uniquely define the phase shift at all. So that we are just using the complex numbers as tools. Same thing here. Good. So that actually what the 4-point running average filter looks like in Z-plane, meaning the zero pole plot or Argon's diagram. And the marking is such that 0 points are marked by O, like 0, and crosses are for poles, for historical reasons. All right, and I already told you about this one, zeros and poles and stability, since we have these 4 properties: linearity, stability, time shift invariance, and causality. If it's a linear and time shift invariant system, then it looks like this. If it's causal or not, well, you can actually take a look at the index. If you don't have any advanced operations for the data, then it's also causal. And the fourth question was, is this system stable? And that gives you the stability criteria is quite simple. After you have calculated the zeros and poles, if all the poles are inside of the unit circle, then you have a guaranteed stable system. You can still do the overflow on the calculations, but it's quite hard. You can still saturate your real output for the stable system, but okay, with this stable system, you can actually have a system that has bounded input, bounded output. If it's unstable, meaning you have even one pole outside of the unit circle, then it's guaranteed that it will actually at some point cause overflow on the calculations. No doubt about it. It happens eventually. So stability is a good property. Critically stable systems on digital domain, they are even more critical than in analog domain. How to make nice oscillators. In here you would make a nice oscillator by putting the pole exactly on the imaginary axis. It's hard to do, but okay, there are some tricks how to do it, say. Good approximation. So fundamentally, we put a pole very close to that one and then have a feedback mechanism to pump the energy to the oscillator. Same thing here. You will basically make this oscillator so that you have the real pole very close to the unit circle, but then have a software mechanism to keep the output at certain level. All right. So stability criteria similar to analog systems. When you just think that on analog systems you have the imaginary axis is where your frequency is. Here you actually think of, okay, unit circle is where my frequency is. Inside is stable, outside unstable, on unit circle is critically stable. Zeros can be anywhere. So the location of zeros do not affect on the stability at all, which means practically that if you do not have any feedback, the system is stable. Since it has all the poles are right there at the origo, meaning stable. Wow, that was a loadful. How about having a 15 minutes break? So come back at 3:15.